We're going on a quest to the very edge of reality, really. We're going to explore the ultimate limit of cold and the incredible fundamental law of the universe that says you can't quite get there.
So let's just start with the most basic question you can ask here. How cold can things possibly get? I mean, really, is there a bottom to the thermometer? A point where everything just stops?
Turns out there is, and it has a name: absolute zero. We're talking 0 Kelvin. Now, to put that in perspective, that's minus 273.15 degrees Celsius, or a bone-chilling minus 459.67 Fahrenheit. And this isn't just, really, really cold. This is the coldest possible temperature in the entire universe, period.
So what would even happen at absolute zero? Well, imagine you could drain every last bit of heat energy out of a system. Every single atom, every molecule would settle into what scientists call its ground state. That's its lowest, most stable energy point possible. It's a state of almost perfect, absolute stillness.
Now, reaching this state of perfect stillness sounds pretty straightforward, doesn't it? You just keep pulling out heat. Simple. But there's a catch. As we get colder and colder, we run headfirst into this massive cosmic obstacle, a fundamental property of the universe itself called entropy. So what on earth is entropy? Well, you can think of it as the universe's official measurement of disorder or randomness. It's all about how many different ways, or microstates, the little particles in a system can be arranged. The more options they have, the higher the entropy.
Let's make this super simple. Think about the particles in a gas. They're zipping all over the place, totally random, with countless possible positions. That's a classic case of high disorder, so it has high entropy. But now, picture a perfect crystal. All the atoms are locked into a super precise repeating pattern. They have very few ways they can be arranged. That's a state of very low disorder, and so very low entropy.
Okay, so with this new idea of entropy, our quest to reach absolute zero completely changes. It's not just about getting cold anymore. It's now a quest to completely eliminate disorder, to somehow force every single particle into one single, perfect, lowest energy state. And hey, at first, it looks like we're on the right track. There's a really clear connection here. As you pull heat out of something, you're slowing down the random movement of its particles. They calm down, they settle into place, and the whole system gets more ordered. The entropy starts to drop. It seems like we're headed straight for zero.
So how do scientists actually try to do this? Well, they'll take a substance and mess with something like its pressure or magnetic field to cool it down. And that first step works great. You get a nice big drop in temperature and entropy. Awesome. But then you do it again, and the drop is smaller. And the next time, even smaller. You see the pattern? Each step takes the same amount of work, but you get less and less cooling out of it. It's a classic game of diminishing returns.
And this brings us right to the heart of our whole quest. We're getting closer and closer, but every single step is harder than the one before it. The goal is right there in front of us, but the path to it seems to just stretch on and on and on. So can we ever actually take that final step and get there?
And the answer from the universe itself is a hard no. And this isn't because our technology isn't good enough. Nope. It's a fundamental rule of the cosmos, written into the fabric of reality as the third law of thermodynamics. It's not a suggestion. You could call it the law of impossibility.
And what's so fascinating is how specific the law is. This is known as the Nernst statement. And listen to the language. It doesn't just say it's tough. It says it's impossible to do in a finite number of operations. The universe is literally telling us, go ahead, get as close as you want, but you can never, ever cross that finish line. And that's the whole game right there. Remember that cooling process where each step got smaller and smaller? The math behind it shows that to actually reach absolute zero, you would need to take an infinite number of steps. You can get 99.99999% of the way there, but you can never, ever take that final infinite step.
For those of you who like the math, it all boils down to this really elegant little equation. Here, S is our friend entropy. The KB is just a constant. Don't worry about that. The really important part is ln omega. That's the natural log of omega. And omega, that's just the total number of possible arrangements, or microstates, for all the particles.
And this is where it all clicks into place. At the theoretical point of absolute zero, a perfect crystal would have only one possible way its atoms could be arranged. That single, perfect, lowest energy ground state. Just one. So, in our equation, omega equals 1. And if you remember from math class, the natural log of 1 is 0, which means the entropy, S, at absolute 0 is exactly 0, a state of perfect, absolute, flawless order.
Okay, so if we can never actually get there, if this state of perfect zero entropy is impossible to reach, you're probably asking yourself, so what? Why does this law even matter? Who cares about a destination you can't get to?
Well, it turns out that knowing where 0 is changes everything. The third law gives us a definitive, absolute starting line for entropy. Think about it. It's like trying to measure the height of a mountain, but you have no idea where sea level is. It's impossible. By defining this absolute 0 point for disorder, the law allows chemists to predict whether a chemical reaction will even work or how efficient an engine can be. This so-called impossible law is actually one of the most practical and powerful tools we have for understanding the universe.
So this whole quest for absolute zero, it teaches us that some limits in our universe are absolute. They're hard-coded. We can't reach the coldest temperature possible, just like we can't travel at the speed of light. And it just makes you wonder, doesn't it? What other fundamental, impossible boundaries are out there, quietly shaping the reality we experience every single day?